Hi everybody, I hope that you're all doing well. In this video, I'm going to show you how to conduct a basic data analysis in Stata when you have a quantitative outcome and a qualitative predictor. We're going to pick up with the same thing that I've done in each of these videos, which is run the standard header that you should have in your do files in Stata. I'm going to, again, mostly direct people to the first video in this series that details why we include all of these things. I did only want to call attention to the most important of them, which is that you should make sure that you've changed your working directory to one that actually exists on your computer as opposed to mine. This is on my computer, this pathway here. And it should be a folder where you do actually want to store things in Stata and where you've actually piled the data, in this case, the GSS 2018 is the file we'll be using, into that folder. So make sure that this goes to a place on your computer that already exists, that you know where it is, and that you've put data into. So without further ado, we'll get started, not delaying too much further with any of discussion of this material. But again, that is in a previous video in this series. So let's suppose that we're interested in the relationship between income and whether or not someone is Protestant. In the previous video in this series, which you don't need to watch all the way through, I detailed the construction of a variable called Protestant on the GSS, which is a dummy variable. So that's kind of the theme I'm going to pick up with here. So if you are interested in this type of a project, I would like for you to go ahead and look at the univariate analysis material from the regression video for the ratio outcome here. Ratio is kind of like the purest type of a quantitative variable. And I would also then like for you to look at the univariate analysis for the categorical predictor from the two-way table video. So I'm going to be pretty concise here. But I did want to use this as an opportunity to discuss a common gotcha, not this time a Stata gotcha, but a GSS gotcha, which is that the GSS oftentimes asks questions in a way that might be sort of counterintuitive or might not be as nice as you might like. You'll see what I mean by that in a moment. So let's go ahead and pick up with the income variable on the GSS. And if you are interested in the use of the GSS to record information on people's income, so notably, none of these are a very good measure of income. Let's take, for example, this one here, the one that's just called income. Seems like a good place to start. So let's go ahead and summarize that. And I'm going to pull my window out a little bit here so it's easier to look at. So when we do that, we see that the numbers here seem sort of surprising. So you might think, okay, 10 seems a little bit weird. Maybe what that is like dollars per hour or something. But notice that the min and the max are 1 and 12. And we know that the maximum income is probably not $12 an hour. We could try tabulating it and see if we get any different information. And then what we see is that these are actually brackets. And these brackets are really not very useful because we have these uneven bucket sizes. So here we've got about $2,000. Here we've only got $1,000 for some reason. And then here we have about $5,000. This is kind of a total mess. We really should treat this like an ordinal variable rather than a quantitative one, especially because it's strongly top-coded. So you can see here, the great majority of the sample, of course, ends up in the bucket. Their total family income was more than $25,000, which is not too hard to achieve in the US at this point. So this is not a good variable for use. And probably what this has to do with is the GSS sometimes asking the same questions over time to say, you could somehow use this to look at both the effects of changes to real wages, but also possibly changes to nominal wages or inflation if you keep this question the same from year to year. But it doesn't actually provide a very good measure of someone's actual income in 2022, or in this case, in 2018. So we might go ahead and look around for other variables, but it turns out that most of them are going to have this problem. So we can say, try real income. So here the GSS uses constant dollars, which is a way of getting around the problem of inflation. But we'll see that, again, this is still a fairly discrete variable that takes on only really specific values. So you can see we have 5107.5, but 70 people had exactly that income. That doesn't seem very plausible. And so what's going on there is that these are very likely just scalar multiples of the brackets that they used in the past. So that's not really going to help us out very much. We could review a couple others here. I'll try this one, tab real R inc. right? Still not really getting very much. If we take the code book of all of these things here, so let's try codebook income, real inc, and let's try this one here, R income 16, you'll see that most of these have kind of the same sets of problems, but this one here, R income 16, at least has 26 unique values, so that makes it somewhat more variable than the baseline income variable. So I decided to just use as a measure in this case, R income 16, the respondent's personal income. Even though that's a pretty flawed measure, we also have quite a lot of missing values here as well. This seems like if you're interested in income on the GSS, this is the best way to go about it. For the sake of a project in a class with me, say in Stata 360, you're more than welcome to use this variable and treat it like a quantitative variable because many people are understandably interested in income. But you should note, for the sake of actual knowledge of statistics, that this is a bit of a dodgy technique because we can see here that these are not like just looking at some of these brackets here, the example brackets. This bracket has a different size than this bracket. So this is a classic ordinal variable in that sense. The distance between values is not the same. So this is what's represented by a unit change near 15, but this is what's represented by a unit change near 19. So just a side note there, but you are welcome to use this as it exists in the GSS for my class. So we can still take some basic information about our variable. So we already pulled the code book, but let's go ahead and tabulate it one more time. And we can see that these buckets here are somewhat unwieldy, but they're at least a little bit more evenly spread out. So we don't have that very strong top coding. There's not very many people who end up in the highest bracket here. So that's at least a mild improvement. We can go ahead and print our basic summary statistics, although notice that these are not necessarily going to be very meaningful. So we could look at the mean and the median here. In this case, we get this funny fact that according to the simple definition of skew, we would actually have here left skewed data because the mean is less than the median, aka the 50th percentile. But we know that income in the actual United States is strongly rightward skewed. In other words, there's very high upper end outliers. So this is in many ways going to be kind of a flawed measure. But again, I just mentioned this and license its use because many people will want to use the GSS and will be interested in income. Okay, so that's more or less what we would want to do for the sake of a numeric analysis of income. Now, I've already talked in a previous video about our predictor here, which I think is not a bad idea to consider. That is making a dummy variable when you are considering doing an analysis of this type. One, because they're well suited for regression analysis. And two, a lot of times you're really just interested in a pairwise comparison. So you might want to try to think about breaking up your outcome variable or your predictor variable, pardon me, into just two possible values. So if you are interested in trying that approach, just go ahead and see the previous video in this series that goes into some detail on the construction of dummy variables. I'll just highlight a couple of things here. I've already said this part out loud. The thing is that dummy variables have really nice, easy interpretations. So the mean is the proportion of observations taken on a 1. That's a pretty easy proof. You might try it on your own. The basic point is that if you sum up the variable, all the people who are zeros sum to 0. So the sum is just 1 plus itself times the size of the subsample who are 1s. So in other words, you just get n for the subsample who are 1s, and then you divide by n. So that just gives the proportion of people who are 1s. The variance, this is a little bit harder to prove, although there's a proof in the linked lectures to this, basically for Stata 360, which I linked in these YouTube videos. The variance kind of is theoretically important, so it's roughly equal to the sample proportion p times 1 minus p. There's a small bias term, but for the most part, we don't really need to worry about that. It's more important in a theoretical sense. There's not really that much use in calculating the standard deviation for a dichotomous variable. So without further ado, again, go see the other video on the state of mechanics here. Let's just construct this variable and move ahead. And we can see that about 49% of the sample here were Protestants. That's the main takeaway here. So we can now move on to a graphic analysis. So we will consider our income variable here as something like a highly discrete quantitative variable. It really should be considered a nominal variable if we're being rigorous, but I know that, again, many people will want to use income, and there's unfortunately not a better option on the GSS that I'm aware of. So why don't we put together our kind of basic tool of the trade here and put up a histogram. And we can try using the discrete option to remind Stata that it should be aware that this is a very discrete variable. And here I've got this kind of unique color scheme going. So let's actually fix that here. We'll say set scheme s2 color, which is the Stata default. And we see this, and this is what you'll see if you pull this up. So again, it is notably left skewed, which is, again, not very accurate for real income. And we see this kind of interesting hump at the end of the curve here, indicating some top coding. But it at least gives us a sense of how income coded in this way is distributed. We can toggle the bin width if we want. That's something that I didn't mention in the previous video. In this case, this makes it look a little bit less jagged. So you can play around with bin width as you like. In any case, this is not going to be really that perfect no matter what you do. Finally, we can look at a box plot as well. I've already covered the interpretation of these at some length on the quantitative video, so go see that for more. But as a brief reminder, this here is the median. This is the 75th percentile, aka the third quartile. This is the 25th percentile, aka the first quartile. And then these whiskers here are 1.5 times the IQR, or interquartile range, so this minus this, added to the third quartile and subtracted from the first quartile. And Stata will, generally speaking, not draw the whiskers all the way to that length if the highest observed values of the data are lower than that length. So that's why you sometimes see whiskers that don't seem to protrude quite as far. And here we see some evidence of a left skew. So the median in this case, more than any of the box plots we've looked at so far in this series, is closer to the third quartile than it is to the first, indicating a fairly pronounced left skew. Okay, so let's move on, and we'll, again, just take a pretty basic analysis here for Protestant. This is a variable that's pretty easy to get a handle on graphically. So we just want to go ahead and make a basic bar graph. I will show later on the way into producing publication quality graphics, which you should consider doing for this project. You don't have to go quite as far as I might, but you will want to at least do some things like add a title, consider whether the x-axis, which doesn't actually really exist in this case, but this right here needs to have a change to title, something like that. In this case, this really isn't too bad. So now let's move on to the bivariate analysis, and this is going to be the part that's actually a little bit different than what we've talked about before. So what we're doing in this case is basically we're going to compare group means. That's usually the best idea if you're thinking about relating a quantitative outcome variable to a qualitative predictor. Now, you could carry out other types of project. For instance, you could look at the maximum by group, you could look at the variance by group, but usually those really aren't that interesting relative to looking at the mean or possibly the median. But we're often going to look at the mean because that's what connects this analysis here to more advanced analyses. So a lot of times in statistics, we use the mean even where the median would be more robust because the mean is more tractable in sort of analytic sense. And the reason for that fundamentally is that for many types of distribution, including some types of dummy variables, for instance, the median doesn't always converge when you think about its sampling distribution. So let's talk about a little bit of bivariate analysis. So we are going to just try to find those conditional means. And when I say conditional mean, all I really mean is that the mean, or the average, I'm saying mean a lot, so let's just call it the average temporarily, conditional on whether we're looking at, say, people who are Protestant or people who are not. There's a number of ways to do that. I've shown several in the homeworks for this class that I won't even show here, but here's a way that I think is maybe the nicest looking. And it also gives me the opportunity to briefly tell you about an interesting Stata utility. So why don't we put these into a table and fill the table in with the mean of income here. So the Stata utility that I'm talking about is this version 16. So Stata actually, in my opinion, kind of badly degraded the table command in version 17. Progress is not always linear. in any part of life, but programming is no different. And it also changed the syntax. And so since a fair number of people in our class are probably using version 16 and others version 17, I'm just going to benchmark this explicitly. Even if you have version 17, you can use version 16 commands. So we're going to write vers 16 for version 16, colon, and then we'll run the command. And we're going to say table Protestant, which is a little bit different than tab. So tabulate and table are slightly different. And table lets us more easily fill in the table, the frequency table, with this mean, or these means, actually, to be most precise. So let's do that now. And we'll inspect our results. And we see here that we get a nice comparison. And it looks like non-Protestants, generally speaking, have a slightly higher income. So there's not a very pronounced difference, but that's okay. It's okay to have null results. The main point is that we here just want to make sure that we've done the kind of analysis we want to do. So this is pretty simple. And in principle, that's really all that you need to do. Now, I do want to let you know, though, that when you do construct a dummy variable, this won't work if you don't have a dummy. You have another kind of qualitative predictor, you should stop at this point. But if you do have a dummy variable, you can take the correlation coefficient with a quantitative outcome. And we can go ahead and do that right now. And you can see here that we get numbers that there's not a very strong correlation, but this actually is meaningful in the case of a dummy variable. And the reason for that is that dummy variables, as noted in my lectures, ameliorate the two big problems of nominal variables, or qualitative variables generally, I should say, in quantitative analysis. The first and more obvious one is that for nominal variables, the most qualitative type of variable, there really is no sense of how to order the variables, right? Or the values of the variable, I should say. So we can't order the possible values of religion, but there's obviously an order to the possible values of Protestant. 1 is more Protestant than 0, so that's fixed. Then the second problem is that even for an ordinal variable, so something like a classic Likert item, the problem is that there's not a common distance between the values of the variable. But again, for a dummy variable, because there is only one distance, so to speak, from 0 to 1, there's not really the problem of having to compare that distance to some other distance. So 0 to 1 means you flip on the switch from not a Protestant to a Protestant. That's maybe feeling a little bit inexact, I could understand, but you can see how that definitely seems a little bit less dodgy than having some kind of ordinal variable where you've got 10 different responses, but they all have different kind of gaps between them, so to speak. So that's the correlation coefficient. We would say there appears to be a fairly small negative relationship between the two, which is also what we found just kind of in a different way by calculating the group means. But the more common way to use a quantitative technique with a dummy variable is to do a regression on a dummy variable. And again, you can't really do this if the variable is truly nominal. And if the variable is ordinal, you should be super careful. That's kind of what we have here. But because this is a true dummy variable, we can use it. Now, if you do have a nominal variable, like religion, you can actually very easily in Stata, using what's called factor variable notation, convert relig to a whole set of dummy variables. So you don't really, in the end, like have to do that much at a higher level. So if you want to enter in religion into a regression analysis, you can actually enter in every possible value basically as a separate dummy variable with just a couple of keystrokes. So in a way that doesn't require you to actually make by hand a whole bunch of dummy variables. So you can, in a certain sense, record the information in a variable like religion without throwing out that much information. So you can actually use all of those different possible values as dummies, but that takes us into multiple regression, and that's a little bit beyond where this analysis is. So for now, focus on the problem of coming up with a dummy variable that is just a single predictor, so a single thing you want to break people up into. And by the way, that's often a good exercise anyway, to think about how can I compress the information in my data set. Compressing information is an art, but there are certainly problems in having data that are too coarse or too fine-grained, and finding the balance is part of doing math at a higher level, or statistics, I should say. So let's now calculate that regression equation. And as a reminder, a lot of this might look a little bit scary at first, but here are the main things we care about in this regression equation. first, we care about the coefficient here. Second, we care about the constant. Third, we care about the r squared. So in this case, it actually makes more sense to begin with a constant. And the reason for that is that if we write out that regression equation for a dummy variable, and remember that that just looks something like this. So we're going to say y equal to beta naught plus beta 1 times d. When we do that, we are basically remembering that d only takes on two values. So what happens if d is 0? So that would be where we have a constant only in the model, and that also represents the values for people who are zeros in the dummy. So that would mean our model for those people is y equal to beta 9. And if you think about, if we're just looking at one value of the data set, and we know there's points that spread around that value, what point is going to minimize that spread? And you might know that the mean is a least squares estimator. And so you might know that to pick the best possible value for the regression line to fit through at that point, we would pick the mean as the value for that to flow through. Now, that trick doesn't always work, of course, because for other data sets, you've seen, or at least if you're in my class, you've seen that sometimes regression lines, when the underlying data really aren't that linear, can sometimes totally avoid passing through the obvious mean for a particular value. So sometimes it systematically overshoots or undershoots because all that's required, or really all that is a product of OLS, is that the residuals have no overall relationship to the value of the predictor. So there's no covariance overall between the residuals and the predictors, but that doesn't mean that there can't be places where there's clearly some kind of relationship. The residuals are systematically overshooting or undershooting. So what that means is that when we don't have that many values, though, we really can't have this problem of nonlinearity in a certain sense when there's only two possible values of the predictor. So it's actually the case that we can just say, sure, the regression equation should pass through the conditional mean, or the regression line should pass through the conditional mean at beta naught and at beta 1. So what that would mean in this case is the constant's just going to be the value of the mean for the 0 group. Now, if we plug in the 1, what does that tell us? We're also going to say that this here should be, if we write this out, this should be the expected value of y, given that d is equal to 1. And what that is just the group mean for these people. And by the way, here I'm just using the command window to write stuff. This doesn't have any programming meaning. So if this is going to be equal to the regression equation, we remember that we already decided that beta naught was going to be the mean for the 0 group. So we'll write that as expected value of y given that d is equal to 0. And now if we solve for beta 1, we can just delete this 1, move this over here. We're going to get this equals our regression slope. And so that demonstrates that the slope for dummy variable regression is the difference between the mean for the 1 group and the mean for the 0 group. And we can also check that out here. So let's display this here. So let's say display this, this here minus this. And if we go ahead and take that set of basic summary statistics again, so we say by sort R income 16, some Protestant, did that backwards. By sort Protestant, some R income 16, we see we get 15.49 basically for Protestants, and then 15.74 basically for non-Protestants. And if we come back up here, sorry, there's a lot of output to scroll through now. But if we come back up here, we'll see we got 15.74 for non-Protestants and then 15.49 for Protestants. So that matches exactly what we got by hand. So that's a demonstration that that is the meaning of progression on the dummy variable. And we can interpret this in the same way that we always do. So the coefficient here represents a unit change in the value of the predictor. So in this case, the unit change in the value of the predictor means you are sort of flipping on the switch of the dummy variable. That's a common kind of metaphor. So we are thinking about the change associated with the reference category, or in other words, the zeros, to the included group, or the group Protestant here. So it's the group difference in means. And then here, I wrote a little bit of justification for that. You can also think about the proof as well. The proof is actually relatively simple. The idea is basically this. If you recall that the covariance or the beta hat, so OLS regression in the bivariate case can be thought of as the covariance between x and y over the variance of x, then you recall that the variance of x is almost p times 1 minus p mentioned above. Partition the covariance into two sums. So one sum is going to be for the zeros, one for the ones. Sum for the zeros is negative p times n for the zeros times y bar for the zeros. The sum for the ones is 1 minus p times n for the ones times y bar for the ones. You rewrite the subgroups as basically 1 minus p times n and p times n, and then the rest is basically algebra. So that proof is also given in full in the associated lecture notes, so feel free to see that. Finally, let's talk about the bivariate graphical analysis. So we have a couple of options here. One, we could technically show a scatter plot. I want to actually show that first because it's not very useful. So let's look at that here. And you can see that this is not super informative. We didn't bother adding a jitter. We didn't bother cleaning this up. So maybe that's on us. But fundamentally, we can see that this is not going to be very interesting to look at in any case. And that's because this is a case where regression makes perfect sense numerically, but the nature of the data means that this is just not the right kind of an approach here. We just have far too discrete a predictor in this case. So let's go ahead and now think about an alternative that might be superior. So we could go ahead and just pull up a bar graph of means. And before we saw that the bar graph command sometimes has this funny gotcha, but if you write graph bar and then the variable, you get results that just take the mean of that variable. But you might want a bar graph, for instance, of Protestant itself. So that's why we didn't write something like graph bar, say relig, because remember that this just produces the mean of relig, which is really kind of meaningless. So what we do here is say graph bar r income 16. That's the main thing that we want, the thing that we want the mean of over Protestant. If we do that, we see that we get basically the same results that we got in the numeric analysis. So this is nice. What we do want to do, though, is clean this up a little bit. So I'm going to show this and then explain the code in a moment. So this is a little bit nicer looking. And you can see that what this does is, first of all, rotates it horizontally so that these are a little bit easier to compare the heights of. It adds a title here. We affect the title a little bit down here as well. So we clarify that this is the GSS scale. We add a note giving the source of this thing. And you can even play around with the schemes as well. So I've discussed schemes in that publication quality graphics video. Let's try changing the scheme to this one I've been messing around with lately, GG hue, which is based on R's kind of GG plot routine. And I think this looks even a little bit nicer. These pastels are really nice, in my opinion. So this is a fine way to prettify the graph. Let's talk a little bit about how we did that. I'll actually explain this line of code here in a moment. But first, what we do is use the same basic syntax. We write H bar in place of bar to make it horizontal. Then we add a title here. So status default is not to include titles. So we just put the title in quotation marks. Notice that we're using these line extenders, these 3 forward slashes, to make sure that the program knows that we want to consider this line, this line, this line, and this line as part of the command. Otherwise, it will assume that the end of a line means the end of a command. We also modify the title size. So we add a comma here within the title and make the size medium. We add a note here. We add a Y label. So we're basically going to have Stata tick the Y axis a little more frequently than it would do by default. And then we're going to add a Y title as well. So this is all pretty straightforward. I'll walk through the exact grammar here, but you can basically imitate this and it'll be helpful. Finally, the last thing to note, I promised I would explain this bit here. So we're doing this to basically get the N. So we're saying count if basically the person is not missing on Protestant and income. And what that does is basically put into Stata's working memory a bit of a return value. And a return value is very much like the concept of the answer from your high school calculator, in that it is a value that is in Stata's sort of short-term working memory and can be invoked. It can't be invoked after a certain, well, after you run any other commands, because otherwise Stata's memory would just explode basically. But it's oftentimes handy if you want to refer back to a previous command to do that. The syntax is generally that you write R for return and then in parentheses the thing you want. Here that's just N. These tick marks here are kind of unique. And basically what they do is they, without getting too deep into the discussion of macros, which I talked a little bit about in my graphics video, what these do is basically tell Stata, this is going to be a little bit of code, because otherwise this is inside of a string. It's inside of these quotation marks that tell Stata to print this as basically as text. But we want Stata to actually try to read this part in the way it knows how to read, so to speak. And so we put this left tick here and this right tick here. Notice that these are different. And what that does is pull the basically the result from this command here. So we can actually just look at that directly. If we type this here, we can also just display that value here, right? So we can say display RN. And in this case, we don't need to write those special ticks because we're not putting in a string, but we could do that here. So we could say display RN just like this. And this is why we're writing this like this. And you can see it prints it like this. But if we don't have those ticks, we'll get this output. And we just get RN right back because these strings delimiters, basically the quotation marks, tell Stata, hey, consider the next thing that happens to be not code, but a string of text. If you really don't bother with all that, you can also just look up the N in a variety of different ways. For instance, by writing down tabulate Protestant sum R income 16. And we get the total frequency here. And so you could just write down that number and then print it by just going here and literally writing it in. So that's where I'll wrap up this video here. Hopefully this was interesting and rigorous and informative. I hope you all continue on with Stata. Thanks for watching.